August 8, 1938, Bridgeport, Connecticut. European engineering consultants would dismiss what they witnessed rolling out of Magnus Wahlstrom's modest factory that morning. A $995 vertical milling machine that defied every principle of precision manufacturing their universities had taught them. Through the industrial haze of Depression-era Connecticut, American machinists operated equipment that European experts declared fundamentally impossible. No massive foundations, no $7,000 horizontal mills, no elaborate cooling systems or electronic controls. Yet this simple machine maintained accuracy that German imports costing 8 times more could not match. In European factories, precision required massive cast iron monuments weighing tons, anchored to concrete foundations, monitored by engineers with advanced degrees. The Americans were building accuracy into machines using techniques European schools had abandoned as primitive: hand-scraped surfaces, mechanical backlash elimination, cast iron thermal mass, methods that created microscopic oil pockets lasting decades, while modern ball screws drifted out of tolerance monthly. 4,000 miles from European engineering schools, the most unlikely manufacturing revolution was proving itself, not through complexity, not through electronic compensation, but through Swedish immigrant Rudolf Banno's radical belief that American simplicity could achieve what European sophistication could not. The paper bag crinkled under Rudolf Banno's calloused fingers as he sketched what every engineering textbook insisted could not exist. Outside his delivery truck, the Connecticut Manufacturing Company's smokestacks belched black clouds into the October sky of 1936, but Banno's attention focused entirely on the mechanical drawing taking shape between grease stains and coffee rings. 49 years old, with the methodical patience of a man who had spent 36 years in American machine shops, he traced the outline of a vertical milling machine that would cost less than $1,000 and hold tolerances European engineers swore were impossible at any price under $7,000. The sketch showed a radical departure from accepted wisdom. Where European horizontal mills required massive cast iron beds weighing 8 to 12 tons, Banno's design called for a compact vertical spindle mounted on a column no bigger than a telephone pole. Where German engineering demanded elaborate foundations extending 6 feet into reinforced concrete, his machine would bolt directly to a factory floor. Most heretical of all, where established manufacturers insisted precision required imported components machined to tolerances measured in 100,000ths of an inch, Banno's design relied on techniques American pattern makers had refined in thousands of small shops across the industrial Northeast. The impossibility of his vision had been explained to him repeatedly. Frederick Holtz, chief engineer at Cincinnati Milling Machine Company, had stated the mathematical certainties during their correspondence earlier that year. Vertical spindles created inherent instability. The cutting forces generated by a rotating tool would deflect a vertical column beyond any hope of precision. Thermal expansion from the spindle motor would cause dimensional drift measured in thousandths of an inch. Without massive horizontal construction and temperature-controlled environments, no milling machine could maintain the 1,000th inch accuracy that American manufacturing increasingly demanded. Yet Banno had spent the morning watching Cincinnati's own $7,000 horizontal mill lose tolerance at precision tool and die across town. The machine's elaborate ways, ground to mirror finishes by German craftsmen, had developed wear patterns that required constant adjustment. Its massive structure, designed to eliminate vibration, had proven so rigid that minor settling in the building's foundation translated directly into spindle misalignment. The temperature compensation system, a marvel of European engineering, struggled with Connecticut's humidity fluctuations and required daily recalibration by a specialist earning more per hour than most machinists made in a day. Banno sketched faster, his mind racing through solutions that violated every principle he had learned during his apprenticeship in Swedish machine shops. Instead of fighting thermal expansion, why not embrace it through careful material selection? Cast iron expanded at half the rate of steel, and properly designed castings could maintain dimensional relationships even as temperatures changed. Instead of pursuing perfect surface finishes, why not create controlled imperfection that served a purpose? Hand-scraped ways, with their thousands of microscopic oil-holding pockets, provided lubrication that lasted decades while ground surfaces starved for oil within months. The breakthrough had come to him during a conversation with Tommy Kowalski, the Polish hand scraper whose father had taught him techniques European schools now dismissed as primitive. Tommy had shown him a 1908 Cincinnati mill, its ways scraped by craftsmen trained in the previous century. After 28 years of continuous operation, the machine still held tolerances that modern ground surfaces lost within their first year of service. The secret lay not in the precision of the scraping, but in its calculated imperfection. Each scrape mark created a tiny reservoir for lubricating oil, and the pattern of these reservoirs distributed loads across the entire bearing surface rather than concentrating stress on a few high points. Banno's pencil traced the tapered gib system that would eliminate backlash without electronic feedback. European engineers solved positioning problems with complex mechanical computers that sensed spindle location and adjusted for thermal drift. His design would prevent drift mechanically, using tapered steel wedges that could be adjusted by hand as components wore. A machinist could eliminate backlash by simply tightening two bolts, no electronics required. The economics were equally radical. Cincinnati's horizontal mills required specialized installation teams, reinforced foundations, and climate-controlled environments. Total installation costs often exceeded the machine's purchase price, limiting precision manufacturing to wealthy corporations that could afford both the equipment and the infrastructure it demanded. Banno's vertical design would ship complete on a single railroad car and bolt directly to any concrete floor strong enough to support a standard lathe. He folded the paper bag carefully and slipped it into his jacket pocket as Magnus Wallström approached the truck. His Swedish compatriot carried the methodical skepticism of a man who had survived the Depression by avoiding expensive mistakes. But Banno recognized the curiosity in his eyes. Wallström had built his small manufacturing business by identifying opportunities that larger competitors overlooked, and he possessed the practical engineering knowledge to evaluate innovations that existed only on paper bags. Their partnership would formalize 3 months later, but the handshake they exchanged that October afternoon committed them both to proving that American ingenuity could triumph over European capital. Wallström would provide the manufacturing expertise and financial backing. Banno would contribute the design and the unwavering conviction that simple solutions often proved more durable than complex ones. The first prototype would emerge from Wallström's shop in July of 1937, a machine that looked deceptively crude compared to the polished perfection of German imports. Its castings bore the rough texture of American foundry work rather than the mere finishes European customers expected. Its controls consisted of simple hand wheels and mechanical stops rather than the graduated dials and micrometer adjustments that proclaimed precision on more expensive equipment. Yet when James Morrison reluctantly agreed to test the machine at Precision Casting Corporation in Syracuse, the impossible began to reveal itself as inevitable. The $995 machine that could not possibly work held tolerances of 1/1000th of an inch across its entire 20-inch table travel, day after day, month after month, while the $7,000 Cincinnati horizontal mill in the next bay required weekly adjustment to maintain half that accuracy. Word traveled through American machine shops with the peculiar velocity of industrial gossip, carried by toolmakers who moved between factories and spread by suppliers who served multiple customers. By the spring of 1940, James Morrison's reluctant endorsement of the Syracuse Bridgeport had transformed into evangelical enthusiasm, and his production reports circulated through manufacturing networks across the Northeast. The impossible machine that cost less than $1,000 was not only holding its advertised tolerances, but improving with age, a phenomenon that contradicted everything European engineering theory predicted about wear patterns and dimensional stability. Tommy Kowalski understood why. Each morning before the first shift arrived at Bridgeport Manufacturing, he entered the assembly area carrying his canvas roll of spring steel scrapers, their edges honed to precise angles that no machine could duplicate. The tools represented 4 generations of Polish craftsmanship, passed from father to son, along with the tactile knowledge that separated true artisans from mere technicians. Tommy's fingers could detect surface variations measured in 10,000ths of an inch, and his scrapers could remove metal in controlled amounts that precision grinding wheels could never match. The hand scraping process began after each machine's casting had been rough machined to within 5/1000ths of final dimensions. European manufacturers would complete the surfaces with grinding wheels that created mirror finishes measuring 8 micro-inches roughness average, surfaces so smooth they appeared flawless under magnification. These ground surfaces made impressive demonstrations for potential customers, but they created a fundamental problem that European engineers had never solved successfully. Tommy spread a thin coating of Prussian blue across the rough machined way, then positioned a precision straight edge and applied carefully controlled pressure. When he lifted the straight edge, the blue transferred only to the highest points on the surface, creating a pattern that revealed exactly where metal needed removal. European grinding achieved uniform contact across the entire surface, but uniformity was the enemy of lubrication. Oil needed somewhere to hide during the compression cycles of normal operation, and perfectly smooth surfaces provided no refuge for the lubricant that prevented metal-to-metal contact. The spring steel scraper removed metal 1/10,000th of an inch at a time, creating tiny crescent-shaped pockets with each carefully controlled stroke. Tommy worked in a rhythm established by decades of practice, checking his progress with the straight edge and Prussian blue after every dozen strokes. The pattern that emerged looked random to untrained observers, but it followed principles that master scrapers guarded as trade secrets. 12 to 15 contact points per square inch provided optimal load distribution while maintaining adequate oil retention. Too few contact points concentrated stress and caused premature wear. Too many eliminated the oil pockets that made the difference between a bearing surface that lasted months and one that endured decades. The mathematics of hand scraping defied European precision philosophy. Modern surface analysis equipment could measure the grinding wheel's 8 micro-inch finish with scientific accuracy, but the scraped surface's controlled roughness of 32 micro-inches actually performed better under load. The ground surface's uniform contact pattern distributed forces evenly, but starved for lubrication. The scraped surface's irregular pattern created stress concentrations at each contact point, but the oil trapped in adjacent valleys prevented metal-to-metal contact even under maximum loading conditions. Frederick Holtz visited the Bridgeport factory in August of 1941, ostensibly to investigate reports of American machines outselling German imports in precision applications. His inspection focused on the hand-scraping operation with the intensity of a man whose fundamental beliefs were under assault. European grinding technology had evolved through centuries of scientific advancement, reducing surface roughness from the crude tool marks of medieval craftsmen to the mirror finishes that represented the pinnacle of manufacturing sophistication. The Americans were deliberately moving backward, embracing surface textures that German apprentices learned to eliminate during their first year of training. Tommy demonstrated the scraping process with the patience he reserved for skeptical engineers, explaining through hands-on examples rather than theoretical discussions. He showed Holtz how the spring steel blade flexed to follow the work surface, removing only the metal that needed removal while leaving valleys for oil retention. He demonstrated the Prussian blue technique that revealed high spots invisible to precision measuring instruments. Most importantly, he produced wear pattern data from machines that had operated continuously for 3 years without losing accuracy, their scraped ways still maintaining the oil film that prevented deterioration. The German engineers' objections followed predictable patterns. Hand scraping introduced human variability that scientific grinding eliminated. Surface roughness measurements confirmed that scraped finishes were primitive compared to ground surfaces. Temperature variations and humidity changes would affect the scraper's cutting action, creating inconsistencies that precision manufacturing could not tolerate. Most fundamentally, skilled hand scrapers were becoming extinct as industrial education emphasized scientific methods over craft traditions. Tommy's response challenged European assumptions about the relationship between precision and perfection. The variability that Holtz criticized was actually the system's greatest strength. Human judgment adapted to variations in casting hardness and grain structure that grinding wheels encountered as obstacles. The irregular surface pattern created multiple load paths that redistributed stress as components wore, while uniform ground surfaces concentrated wear at their weakest points. Most importantly, the HOR, oil retention characteristics of scraped surfaces, improved with age as microscopic particles became trapped in the valleys and formed a protective layer that further reduced friction. Production data supported Tommy's claims with mathematical certainty that engineering theory could not dismiss. Bridgeport machines scraped in 1938 still held tolerances of 1/1000th of an inch after 2 years of continuous operation. German imports with ground surfaces typically required adjustment after 6 months and major rebuilding after 18 months. The cost differential was equally dramatic. Hand scraping added 12 hours to each machine's production time, but eliminated the expensive grinding equipment and climate-controlled environments that ground surfaces required. By December of 1941, Bridgeport Manufacturing had delivered 8,000 machines to American factories, and field reports confirmed what Tommy's scrapers had promised. The primitive American technique that European engineers dismissed as obsolete was creating bearing surfaces more durable than scientific grinding could achieve at any cost. The explanation lay not in superior American metallurgy or advanced manufacturing equipment, but in the patient application of craft knowledge that industrial education had abandoned in pursuit of theoretical perfection. The war orders arrived at American machine shops with an urgency that transformed production schedules overnight. December 7, 1941, had shattered any illusions about America's industrial preparedness, and by January of 1942, aircraft engine manufacturers faced tolerances that made peacetime precision seem primitive. Pratt & Whitney's R2800 double wasp engines required cylinder bore accuracies of plus or minus 2/10,000ths of an inch. Tolerances that pushed even the most sophisticated European equipment to its operational limits. James Morrison found himself managing 3 shifts at Precision Casting Corporation, his Syracuse factory running 24 hours a day to meet Navy contracts that specified delivery penalties measured in thousands of dollars per day. The Cincinnati horizontal mill that had anchored his precision operations since 1936 struggled under the relentless production demands, its elaborate temperature compensation system failing to maintain accuracy during the rapid heating and cooling cycles of continuous operation. The German-engineered machine had been designed for the measured pace of peacetime manufacturing, with scheduled maintenance windows and controlled environmental conditions that wartime production schedules could not accommodate. The Bridgeport vertical mill, relegated to secondary operations when it first arrived in 1938, gradually assumed responsibility for the most critical machining operations as the Cincinnati's limitations became apparent. Morrison discovered that the American machine's mechanical positioning system actually performed better under the thermal stress of continuous operation than the European mill's sophisticated electronic controls. The fundamental difference lay in their approaches to the physics of thermal expansion, a phenomenon that became critical when machines operated without the cooling periods that peacetime schedules had provided. Magnus Wahlstrom had anticipated this advantage when he designed the Bridgeport's mechanical backlash elimination system. European engineers solved positioning accuracy through electronic feedback loops that sensed spindle location and corrected for thermal drift using servo motors and precision encoders. The system worked flawlessly under laboratory conditions, but it required the machine to predict thermal expansion patterns based on operating temperature measurements taken at discrete points throughout the structure. When heat distribution became uneven during rapid production cycles, the electronic compensation system struggled to track the complex thermal gradients that developed within the machine's massive castings. The Bridgeport eliminated thermal positioning errors mechanically rather than electronically. Tapered steel gibs, machined to angles measured in minutes of arc, wedged between the machine's moving components and its fixed structure. As thermal expansion occurred, the components grew uniformly in all directions, and the tapered gibs maintained constant contact pressure regardless of dimensional changes. When wear developed after thousands of operating hours, machinists simply tightened the jib adjustment screws to eliminate any looseness that had developed, restoring the machine's original positioning accuracy without electronic recalibration. The physics of the system contradicted European engineering philosophy in fundamental ways. German designers pursued absolute dimensional stability through massive construction and environmental control, believing that thermal expansion represented a problem to be eliminated rather than accommodated. American engineers accepted thermal expansion as inevitable and designed mechanical systems that functioned accurately despite dimensional changes. The difference became critical during wartime production when machines operated continuously without the controlled conditions that European designs required. Frederick Holtz visited American aircraft factories in the spring of 1943 as part of a German engineering delegation studying American production methods. His reports to Cincinnati Milling Machine Company headquarters described manufacturing techniques that achieved productivity levels German theory insisted were impossible without sacrificing precision. American factories operated sophisticated machinery in uncontrolled environments, achieving accuracies that German equipment could match only under laboratory conditions. The Bridgeport machines particularly puzzled Holtz because they violated fundamental principles of machine tool design while delivering superior performance under the most demanding conditions. Their lightweight construction should have resulted in vibration problems that destroyed surface finishes and dimensional accuracy. Their mechanical positioning systems should have accumulated errors that electronic feedback could prevent. Their cast iron construction should have suffered dimensional instability that steel structures avoided through superior thermal characteristics. Yet production data from American aircraft factories demonstrated exactly the opposite results. Bridgeport machines maintained positioning accuracy of plus or minus 5/10,000ths of an inch after operating continuously for 18 months without major maintenance. German horizontal mills typically required adjustment after 6 months of normal peacetime operation and complete rebuilding after 12 months of wartime production schedules. The American machines' mechanical systems actually improved with age as components wore into perfect conformance with each other, while electronic systems accumulated errors that required increasingly frequent recalibration. The explanation emerged through careful analysis of thermal expansion characteristics. Cast iron expanded at 6 millionths of an inch per degree Fahrenheit, while steel expanded at 12 millionths per inch per degree. During normal operation, machine tools experienced temperature variations of 20 to 30 degrees Fahrenheit, creating dimensional changes that electronic compensation systems struggled to predict accurately. The Bridgeport's cast iron construction minimized these changes while its mechanical adjustment systems accommodated whatever expansion did occur without losing positioning accuracy. More significantly, the American approach to backlash elimination proved superior to electronic positioning under dynamic loading conditions. When cutting forces varied during machining operations, the mechanical gib system maintained constant contact pressure between moving components. Electronic positioning systems sensed component position but could not prevent momentary separation under varying loads, creating microscopic movements that accumulated into measurable positioning errors over extended operating periods. By September of 1943, American aircraft production exceeded all pre-war projections, and the precision required for turbine engine components pushed manufacturing tolerances to levels that European equipment could not maintain reliably. Bridgeport machines, designed for the modest requirements of Depression-era job shops, found themselves producing components for jet engines that demanded accuracies measured in 100,000ths of an inch. The mechanical systems that European engineers had dismissed as primitive proved capable of precision that electronic controls could approach only under ideal conditions. The war's demands had revealed a fundamental truth about machine tool design that peacetime manufacturing had obscured. Complexity did not guarantee superior performance, and electronic sophistication could not compensate for mechanical limitations. American manufacturing succeeded not through superior technology, but through engineering approaches that prioritized reliability and maintainability over theoretical perfection. The simple machines that could be adjusted by any competent machinist outperformed sophisticated equipment that required specialists and controlled environments to function properly. The post-war boom brought prosperity to American manufacturing, but it also introduced thermal challenges that peacetime production had never revealed. Consumer demand for automobiles, appliances, and industrial equipment pushed machine shops to production levels that exceeded even wartime schedules, and the continuous operation exposed fundamental differences between American and European approaches to thermal management. By 1947, factories that had celebrated their wartime production achievements found themselves struggling with dimensional accuracy problems that stemmed not from wear or mechanical failure, but from the physics of heat transfer in rapidly cycling manufacturing environments. Rudolph Banno recognized the problem during a visit to Ford's River Rouge complex in the summer of 1946. The massive production facility operated machine tools around the clock, and the thermal loads generated by continuous cutting operations created temperature gradients that no pre-war engineer had anticipated. European horizontal mills, designed for the measured pace of traditional manufacturing, suffered dimensional drift that required constant adjustment as their steel structures expanded unevenly. Electronic compensation systems, calibrated for gradual temperature changes, could not track the rapid thermal cycles that occurred when machines alternated between heavy cutting loads and idle periods. The Bridgeport machines scattered throughout the Ford facility maintained accuracy that puzzled production engineers who understood thermal expansion theory but had never observed its practical effects under extreme operating conditions. Cast iron's lower expansion coefficient provided only part of the explanation. More importantly, the American machines' thermal mass distributed heat more evenly throughout their structures, preventing the localized hotspots that caused steel machines to warp out of tolerance. Magnus Wahlstrom had studied this phenomenon extensively during the war years, conducting temperature measurements on machines operating under various load conditions. His data revealed that steel machine tools developed temperature differentials of 15 to 20 degrees Fahrenheit between their heated spindle areas and their relatively cool bases. These gradients created internal stresses that deflected the machine's structures by amounts measured in thousandths of an inch, deflections that electronic positioning systems could sense but could not prevent. Cast iron behaved differently under thermal stress because of its superior heat-conducting properties and higher thermal mass. The Bridgeport's heavy castings absorbed heat from the spindle and cutting operations, then distributed that energy throughout the entire machine structure before radiating it to the surrounding air. Temperature differentials remained below 5 degrees Fahrenheit even under the heaviest cutting loads, and the resulting dimensional changes occurred uniformly throughout the machine rather than creating localized distortions. The advantage became critical when production schedules demanded rapid transitions between different types of work. European machines required 30 to 40 minutes to thermally stabilize after significant load changes, during which their positioning accuracy drifted beyond acceptable tolerances. American machines reached thermal equilibrium within 10 minutes and maintained dimensional stability throughout the transition period, allowing production schedules that European equipment could not accommodate. Frederick Holtz confronted this reality during Cincinnati Milling Machine Company's post-war market research, as reports accumulated from customers who had replaced German horizontal mills with American vertical equipment. The technical explanations challenged fundamental assumptions about precision manufacturing that had guided European engineering for decades. Massive construction, which German theory identified as essential for accuracy, actually created thermal problems that lighter American designs avoided through superior heat distribution characteristics. The physics became undeniable when measured systematically. Ball screws, the heart of European positioning systems, expanded 12 millionths of an inch per degree Fahrenheit. A 20-inch axis could grow 5 thousandths of an inch just from normal operational heating, and electronic compensation systems struggled to predict these changes accurately because heat distribution was never uniform. The screw's center typically ran hotter than its ends, creating expansion patterns that varied with load conditions and ambient temperature. Bridgeport's mechanical positioning systems eliminated these problems through design approaches that accommodated thermal expansion, rather than attempting to compensate for it electronically. Lead screws machined from cast iron expanded at half the rate of steel ball screws, and the tapered gib systems maintained positioning accuracy regardless of thermal growth. When expansion did occur, it affected all components proportionally, preserving the geometric relationships that determined positioning accuracy. More significantly, the American machine's thermal characteristics actually improved with continuous operation. Extended running periods brought the entire structure to uniform temperature, eliminating the thermal gradients that cause positioning errors during warm-up cycles. European machines suffered their worst accuracy problems during the thermal transitions that occurred at the beginning of each production shift, when electronic compensation systems attempted to track rapidly changing expansion patterns. Production data from General Motors' Flint facility documented the practical consequences of these thermal differences. Bridgeport machines maintained positioning accuracies of plus or minus 3/10,000ths of an inch throughout continuous operation, while comparable European equipment required hourly adjustment during the first 4 hours of each shift and achieved stable accuracy only during extended production runs under constant load conditions. The cost implications extended beyond simple machine performance. European equipment required climate-controlled environments to maintain advertised specifications, adding thousands of dollars to installation costs and ongoing operational expenses. American machines achieved superior accuracy in uncontrolled factory environments, eliminating the infrastructure investments that European precision demanded. When total cost of ownership calculations included installation, environmental control, and maintenance requirements, the $995 Bridgeport delivered precision manufacturing capabilities at 1/10 the cost of comparable European systems. By 1950, Bridgeport Manufacturing had delivered 50,000 machines to American factories, and field performance data confirmed what thermal physics predicted. The simple American approach to machine tool design, dismissed by European engineers as primitive cost-cutting, produced superior results under real-world operating conditions. Cast iron construction, mechanical positioning systems, and thermal mass design created machines that improved with age, while sophisticated European equipment degraded despite constant maintenance attention. The triumph was complete when Korean War production demands pushed machine tools to operational extremes that revealed the ultimate superiority of American engineering philosophy. Complexity had proven less reliable than simplicity, and electronic sophistication could not overcome fundamental thermal design limitations. The immigrant pattern maker's sketch on a paper bag had evolved into manufacturing equipment that redefined precision engineering through approaches that European technical education had abandoned as obsolete. The Korean conflict ended in July of 1953, but the precision demands it had imposed on American manufacturing never retreated. Jet engine production required tolerances that pushed conventional machine tools beyond their design limits, and the aerospace industry's emergence created markets for manufacturing equipment that could maintain accuracies measured in 100,000ths of an inch across extended production runs. European manufacturers responded with increasingly sophisticated electronic controls and computer-assisted positioning systems, while Bridgeport Manufacturing doubled down on mechanical solutions that had proven themselves under wartime conditions. Tommy Kowalski, now 58 years old and supervising a team of apprentice scrapers, watched the first computer-controlled milling machines arrive at competing factories with the skepticism of a craftsman who had seen technological promises fail under real-world conditions. The new equipment featured digital readouts, automatic tool changers, and positioning systems that claimed accuracies of plus or minus 50 millionths of an inch, specifications that made traditional mechanical machines appear obsolete. Yet Tommy's hand-scraped Bridgeports, some now 15 years old, continued to hold tolerances that the electronic marvels could achieve only under laboratory conditions. The apprentice program that Bano had established in 1948 ensured that hand-scraping knowledge survived the transition to electronic manufacturing. Young machinists learned to read surface plates with their fingertips, feeling variations that precision instruments could measure but could not interpret. They mastered the spring steel scrapers that removed metal in controlled amounts, creating the oil retention patterns that made the difference between bearing surfaces that lasted months and those that endured decades. James Morrison, now plant manager at Precision Casting's expanded Syracuse facility, conducted his own comparison testing between the latest German computer-controlled equipment and the original 1938 Bridgeport that had initiated his conversion to vertical milling. The results challenged everything that modern manufacturing theory predicted about the superiority of electronic positioning systems. The 17-year-old American machine, its ways still bearing Tommy's original scraping marks, maintained positioning accuracy of plus or minus 2/10,000ths of an inch across its full 20-inch travel. The new German equipment featuring ball screws and linear encoders achieved plus or minus 1/10,000th of an inch accuracy when freshly calibrated, but thermal expansion caused positioning errors that accumulated throughout each production shift. The fundamental problem lay in the physics of ball screw systems that European engineers had never solved satisfactorily. Precision ball screws required preloading to eliminate backlash, but the preload created friction that generated heat during high-speed operation. Temperature increases of 20 to 30 degrees Fahrenheit were common during extended production runs, and the resulting thermal expansion created positioning errors that electronic feedback systems struggled to track accurately. The screws expanded unevenly, with their centers typically running 10 to 15 degrees hotter than their ends, creating expansion patterns that varied with load conditions and ambient temperature. Magnus Wallström's mechanical approach eliminated these thermal problems through design principles that accommodated expansion rather than attempting to compensate for it electronically. Lead screws machined from cast iron expanded at half the rate of steel ball screws, and the tapered gib systems maintained positioning accuracy regardless of thermal growth. More importantly, the mechanical systems actually improved with wear as components matched themselves to perfect conformance, while ball screw preloads decreased over time and required increasingly frequent adjustment to maintain accuracy. Laboratory testing at the National Bureau of Standards in 1955 provided scientific validation for observations that practical machinists had reported for years. Bridgeport machines that had operated continuously for 10 years showed positioning repeatability of plus or minus 1/10,000th of an inch, with some individual machines performing significantly better. The hand-scraped ways showed no measurable wear after 300,000 operating hours, their oil retention characteristics having actually improved as microscopic particles became trapped in the scraped valleys and formed protective films that further reduced friction. Frederick Holtz, now Cincinnati's vice president of engineering, faced the uncomfortable reality that American manufacturing techniques he had dismissed as primitive were producing superior results under real-world operating conditions. European ball screw technology represented the pinnacle of mechanical engineering sophistication, but it suffered from inherent limitations that mechanical systems avoided through superior design approaches. The complexity that European customers associated with precision actually introduced failure modes that simple American mechanisms eliminated through fundamental physics. The cost analysis was equally damaging to European competitiveness. A typical German machining center cost $65,000 in 1955, while a comparable Bridgeport sold for $3,800. Installation costs favored the American machine by an even larger margin, since it required no special foundations, climate control, or electronic infrastructure. Total cost of ownership calculations, including maintenance, operator training, and downtime for calibration, showed the Bridgeport delivering precision manufacturing capabilities at less than 1/10 the cost of European alternatives. More significantly, field reliability data demonstrated that mechanical systems outperformed electronic controls under the variable conditions that characterized real manufacturing environments. European equipment achieved its advertised specifications only when operated by specially trained technicians in temperature-controlled facilities with regulated power, supplies, and vibration isolation. American machines delivered superior performance when operated by conventional machinists in typical factory environments, making precision manufacturing accessible to small shops that could never afford the infrastructure that European equipment required. By 1960, Bridgeport Manufacturing had delivered 100,000 machines to customers worldwide, and the company's success had spawned dozens of competitors offering similar vertical mills based on American design principles. The immigrant pattern maker's vision of affordable precision had transformed global manufacturing, proving that engineering elegance lay not in complexity, but in solutions that functioned reliably under real-world conditions. The final vindication came from an unexpected source when German manufacturers began licensing American mechanical positioning technology for their own machine tools, acknowledging that electronic sophistication could not overcome fundamental thermal and mechanical limitations. The techniques that European engineering schools had abandoned as primitive became the foundation for precision manufacturing systems that achieved accuracies their electronic predecessors could approach only under ideal conditions. 85 years after Rudolf Banno sketched his impossible machine on a paper bag, original Bridgeport mills still operate in factories worldwide, their hand-scraped ways maintaining tolerances that modern equipment struggles to match despite decades of electronic advancement. The simple American belief that mechanical solutions could triumph over European complexity had created manufacturing equipment more durable than its designers ever imagined possible.